Yeah. Hello. The slide is visible.
Audible, sir. Audible.
Yeah.
Yes, sir.
Slides. Yeah, is visible.
Yes, sir.
Yeah.
Yes, sir.
So this is this course just for the people who have joined today. This is a basic course on device physics for engineering. How to take advantage of devices for developing electronic systems. So we have seen that basically the role of electronics engineers is to develop electronic systems. And electronic system means you have a set of circuits which performs various functionalities, and those functionalities which those circuits are uh, uh, developed using devices. So that is the hierarchy. So our focus is on semiconductor devices, especially the focus is on microelectronics, that is integrated circuits. But primarily in this paper, we will be dealing with semiconductor devices, that is solid state devices. So, we were trying to understand the properties of the material, especially semiconductor material, which is making it possible for making electronic devices. So in this connection, we have taken conductivity as a figure of merit for comparing or assessing the performance capabilities of three types of materials we have taken: semiconductors, metals, and insulators, basically crystalline solids. Then first is the conductivity. We have seen that the conductivity, there is a marked difference between their conductivity, electrical conductivities. Then another important observation we can make is the temperature variation of the nature of variation of their conductivity with the temperature. For example, metals, the conductivity decreases with the temperature. Semiconductors, the conductivity increases with the temperature. And insulators, there is no significant change even up to the melting point of the material. So this is that is what the nature of variation of conductivity in these three different materials. So in order to understand that, what we have looked into is we have tried to find out what are the factors on which conductivity depends on. We see that conductivity depends on the carrier concentration and the mobility. So, and again, then we were looking into what are the factors on which the carrier concentration depends on. In that connection, we have seen that these materials exhibit energy band structures and with energy gaps, etc. So we discussed about the origin of energy band, how their energy band structures, these three classes of material, how their energy bands are different. Then in the last lecture, we have found a way to find out the carrier concentration in the pure, especially in the because our focus is on semiconductor materials. So we obtained a way to find out the carrier concentration. So that has been the story so far. Now, we have seen that, as I mentioned earlier, we have seen that two factors decides the conductivity. One is the carrier concentration, other one is the mobility. So we have defined the mobility in our earlier discussion. We have defined the mobility as velocity per unit field. That is the mobility we have discussed. So if we want to know the temperature variation of mobility with the temperature, is this definition sufficient? So because it doesn't say anything about the temperature, so that is basically the limitation. So if we want to understand, because we have seen that conductivity varies with temperature, and we have seen that carrier concentration varies with the temperature. Now we want to know whether the mobility is influenced by the temperature, whether any change in mobility take place with the temperature. That is what we want to know. So with this definition, we cannot move forward because it doesn't talk anything about the temperature. So we need to go look into mobility in a more fundamental way. So I will call that mobility as the microscopic mobility. That is what is happening within the material. Just like the carriers, we have seen the microscopic uh, picture. The same thing we are doing. Now, very important thing we need to understand, as I've been repeatedly telling, the carriers are not moving in vacuum. So we have to keep it in mind. Again, another important thing we have seen is like in order to take into account the internal forces, we have introduced a concept known as the effective mass, which will take care of the internal forces within the material. So that is how the carriers are moving with a different mass as compared to the normal mass, because that will take care of the internal forces acting on the carriers. So that is another important concept we have introduced in the. So that again we will be taking it forward. That this effective mass concept will be taken forward, even in the case of when we are going to define the mobility. These are all microscopic parameters which are important in deciding the uh, material properties, especially the electrical properties. So these are. Let us look into the origin of mobility in a microscopic way. So now, even if you assume the classical picture of the electrons at any temperature, they will be having thermal energy. So classical picture means you have electrons are treated as electrons as well, because again in semiconductors we have a second kind of electrical carriers. They are known as holes. So uh, you can identify them as particles. So according to the classical free particle theory, at any energy, at any temperature T, KT will be the KT per degree of freedom. There will be KT units of energy will be there, where K is the Boltzmann constant. Definitely, they are not. Electrons are not stationary. So then that means they are moving with some random velocity. So they are, that is known as the thermal velocity. So when they are moving, since they are not moving in vacuum, they get what is known as in physics, we call it as the scattering. That means interaction with the neighbors take place. And within the a solid material, the interaction can be other uh, carriers, like electrons may come across another electron, or electron may come across holes, or holes may come across another hole or electron. Apart from that, they will come across the other atoms within the within the solid. So that is, they are known as the lattice. Actually, in a crystallography, those atomic core are known as lattices. So lattice is also is also not sitting idle. They will be there will be moving, or there will be having simple harmonic motions. So, quantized lattice vibrations are known as phonons. So very often we will be saying that these carriers will be scattered by phonons. Instead of saying lattice, we will be talking in terms of phonon scattering. So there are low energy phonons. They are known as acoustic phonons. Then high energy, if the vibration frequencies are high, then we talk of optical phonons and things like that. So different materials have different types of phonons, etc. So one thing we need to understand is, so there will be lattice scattering of this, or phonon scattering of these carriers, which will cause uh, change in the direction and the velocity of the carriers. then there can be, we will be seeing, we have not discussed so far of introducing impurities into semiconductor material, but we will be taking it up in the subsequent lectures. So we know that we introduce impurity atoms to control the characteristics of these materials. So there will be impurities. So that impurities will introduce additional scattering of the carriers. So that also going to affect. So they this impurities could be ionized, or there are cases we will be seeing that there are they need not be ionized actually. So both can take part in the scattering process. So you have if no field is applied, you can just see the. I think it is visible. So you can see that electron is starting from position one. It goes to in a because of the thermal energy it is moving, and then it gets scattered. So you can see here, it, it gets scattered. That means all of its energy is lost due to collision. So then again, it goes in a different direction because external energy is picked up. It will go to in this. So then again, it loses its momentum or energy, and then again, so so it is perfectly random, and so that you won't see any net displacement at steady state. So the net current will be zero if there is no electric field. So that is a picture we should keep as far as the semiconductor material is concerned, or a pure electrical conductor is concerned. So you have without any electric field, you don't see any current flowing because the net displacement, because the current is essentially rate of flow of charge, and if the charges are not able to, there is no displacement of the charges, then you don't see any net current. So with no electric field, there is no net current. So even though carriers are moving random within the material, there is no net current. This is a picture we start with. So this is I was talking about this. So you have see actually 3 degrees. 1 degree of freedom will give you kT. So if you have 3 degrees of freedom, this is actually physics. We call it as equipartition, law of equipartition. So the all the degrees will have identical uh, energy. So half kT in one. So 3 degrees of freedom means 3 by 2 kT, and then that is the kinetic energy. So you can equate it to the kinetic energy here. Very important. We have to see that it is the effective mass we are talking of. It is not the free electron mass. It is the effective mass of electron in that particular material, which is not a constant. It depends on the material, and it again it depends on the direction also. But you can say that this average energy 3 by 2 kT is can be equated to the kinetic energy half mv squared. So from using this, I can find out the thermal velocity of the carriers. So using this equation, I can get the thermal velocity. So you can see that depending upon the temperature, or you can at room temperature, you can see that the carriers, the thermal velocity is quite large, 2.3 into 10 raised to 7 centimeter per second. This is the order of the thermal velocity the carriers are having when there is no electric field. But we have seen that since there is no displacement, net displacement of the carriers, so you have under steady state condition, no net current without any electric field. Now the situation is changing. So very important. We introduce the concept of drift, because drift means an additional small preferential directionality is given by the electric field. So and another important thing is this is valid especially for low electric field. So we are applying an external electric field. So they will naturally there will be a electrostatic force acting on the carriers. So you see that here there is a net displacement possible, but here one thing we need to keep it in mind. Even though there is a net displacement at each point, electrons loses its energy completely, again it pick up, and that way, so again it's a kind of random, but it has a directionality, a direction. Since they are electrons, they move in the direction opposite to the electric, because they have negative charges, so they will be moving in the opposite direction of the electric field. That is why you can see a net displacement of the charges or electrons in this direction. So naturally, when there is a net displacement of charges, there will be a current. So there will be a net current. So you can talk of a current density. So we can attribute an average velocity, because I told you at each instant they lose the momentum completely, and then again you start, because the electric field is quite low. So they this low electric field, this is the situation. Because again, I repeatedly emphasize on this point that the carriers are not moving in vacuum; they are moving within the material, where they will be getting scattered by different mechanism. So you have an average drift velocity (vd). So very often we talk of a drift velocity superimposed on the thermal velocity, and at low electric field, the velocity, the drift velocity will be much less than the thermal velocity. So it is a small perturbation to the thermal velocity, and which will give a direction for the carriers. So that is the picture we should keep it in mind. This is a kind of thing. The first case where there is no electric field, so more or less the carriers are reaching, or the same number of, there is no net change in the carrier concentration from one point to another. Net change is under steady state condition is zero. So whereas in the second case, when there is an electric field, you see that there is a net displacement of the carriers, even though it is not a straightforward thing, since there is a large amount of scattering taking place. So, but still you will see, because of the drift of the carriers, you will be seeing a net current flow in the material. So whatever we say is valid for the holes also. So even though I am discussed only for electrons, the same thing we can attribute to holes. Only thing is their effective mass will be different, the charge will be different. Now, so you have said that electrons are losing their momentum. So now we are trying to now what we are trying to do is we are going to get trying to get the microscopic picture of the mobility. So now after each collision, we are saying that the momentum is lost. So now let us see what is the momentum. Momentum is the momentum is decided by the velocity of the carriers as well as the mass. Mass is the effective mass. So the drift velocity and multiplied by the effective mass will give me the momentum. So now, how they are gaining the momentum? They are gaining the momentum through the electric field. So you can see that the force, electric force is Q into epsilon. That epsilon is the electric field, and this is the time, average time between electron scattering events. So this will give me the momentum. So the conservation of momentums demands that they should be equal. So that is so I bring in this, equating these two. Now I can define the drift velocity from the previous equation, that is equating momentums. Now the drift velocity I get like this. Now we can get this expression right. That is how you are getting. Anybody has any idea? Hello, anybody there? Can you tell me how I put mu here?
So Q-T over Mn is a mu constant.
Yeah, actually, velocity over the electric field is the mobility. So you can so that will give me, so that means mobility can be equated to this expression, the second expression, q tau by m is the mobility. So this is the microscopic mobility which we are talking. Earlier we have defined the mobility as velocity per unit field, but here you see that the microscopic material parameter is brought in. Q is the electronic charge, tau is the time between the scattering, and m is the effective mass. So this is the picture we should keep. Similarly for the holes, we can see that there. So you have that is, so this is very important relation, that it is the mobility is decided by these two factors. So we can see that some standard semiconductors we are giving in, since the mass is different, you can see that the mobility, and again effective mass of carriers in silicon, germanium, gallium arsenide, and indium arsenide, and the different material, they are different. So naturally, mobility of electrons in different materials will be different. You can see that for the same electric field, the mobility will be different in different materials. So you can see that gallium arsenide and indium arsenide has quite large value of mobility. Similarly, hole mobility is much less in all the materials. So again, effective mass of holes are much higher than the electron mass, effective mass of electrons. So you expect a smaller mobility for the holes. We'll see that this has consequences in many of these devices. So we'll revisit them. So you need to keep it in mind when you are even at the design stage. So that this electron mobility, hole mobility, etc., are going to be different, and hole mobility is quite small as compared to electron mobility. And some materials have high electron mobilities, so they will be used because mobility is going to decide the speed of the device. So high speed devices can be designed using gallium arsenide, indium arsenide, etc. So especially for microwave applications, etc. Yeah. So that is a, so this is the microscopic picture of the mobility. Any questions?
No, sir.
Yeah. So let us now we have to bring in. We said that different kinds of scattering takes place and how it will influence the mobility. So, so there are multiple scattering events. It is true for metals as well as semiconductor. Any conducting medium, this is possible. So you have seen the lattice vibration, which we called as the phonons. Then impurities. We have deliberately added impurities. Like in the case of semiconductors, we deliberately introduce impurities to control its properties. Then there can be defects, because defects means a discontinuity in the periodicity, because we are considering the crystalline structures. So there can be crystalline structure means there is a periodicity. So there the periodicity may be disturbed. So then we talk of defects. Then so you have seen unit cells or the grains, and there the grain boundaries, there can be difference. Then different vacancies. Then, and very importantly, uh, 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 the crystalline structure doesn't go to infinity. There will be discontinuity at the surfaces. So there again, there will be, it will act as a defect. So any variation from the periodic lattice will contribute to the scattering event. So that all the scattering processes will contribute to a change in the mobility. because we have seen that that is going to affect. We'll see how it is, which parameter will be changed by this. We have seen what are the factors on which the mobility depends on, and then which parameter. Any guess? Which parameter will change? Which parameter of the mobility will change with the scattering? Yes. Basically, we have seen that mobility is decided by the average time between the scattering and the effective mass. Assuming that effective mass is not changed, it will be decided by the time. More scattering means the time will be less. So that will be changing the mobility. Because we have seen, just keep in mind, this is the expression for mobility. Q into tau by m. M is the effective mass. Tau will, so the average time will be changed. So that let us see how when many multiple events are there. So this is known as the Matheson rule when multiple mechanisms occurs. So again, we look into the probability theory. So if only one mechanism is happening, then it's a probability that by that time period dt, how much will be the probability for that is given by dt by tau I, where tau I is the mean time between scattering events due to that particular mechanism. We have seen that there are different mechanisms. So depending upon that, the tau will be is the summation of all that, like one dt by tau I, summation of I. So effective time, you can see that 1 by tau will be decided by all this. I think I have a, yeah, you see this. This is the effective mean time is decided by all the, see, we have shown almost all possible scattering mechanisms like ionized impurities, the neutral impurities, then these are the low frequency phonons, acoustic phonons we talk of, then optical phonons. In the case of gallium arsenide, we talk of polar optical phonons and piezoelectric. That is at low temperature, this kind of phonons. So this different kinds of phonons. Then impurities. We have not considered the surface scattering here. That it also can contribute. But in a bulk semiconductor, we have scattering due to ionized impurities, neutral impurities, the impurities which are not ionized. Then you have low frequency acoustic phonons, and at the high frequencies you have the optical phonons. And in the case of gallium arsenide, you have this piezoelectric phonons and the things like that. So the Matheson rule says that the time will be decided in this effective time. The scattering time will be reduced if multiple events of different types of scatterings are there, and it will be dominated by the lowest of all. And then naturally, it will affect the mobility. So you can see that mobility will be reduced if multiple events are there, and it will be decided by the lowest lowest one. So this is the, so here I have shown only the phonon and impurity combined. All the lattice contributions are put into this, and the impurities contribution is put into this actually. So the mobility, effective mobility is decided by the contribution. So it will be dominated by the lowest, lower mobility. Whichever if phonon mobility is low, or the mobility due to phonons are low, then or phonon scattering is low, that will be dominating. Now we need to understand, as far as the impurity scattering is concerned, typically of see, when the temperature is low, the phonon vibration, the lattice vibration will be naturally low or small, and the number of phonons will be low. So there, the influence of the ionized impurities will be more. So at the low temperature, generally we see the influence of the impurities, and then carriers are also moving at a lower velocity, because we have seen that the thermal velocity also is decided by the temperature. So carriers will be moving slowly. So there will be more time for them to interact with these impurities. So at low temperatures, you see that impurity scattering will be dominating. So whereas at high temperatures, the lattice scattering or the phonon scattering will be there. So this is a picture. So again, one can demonstrate that this is one is the if the impurity scattering, the variation of impurity scattering with the temperature is in this fashion, the impurity scattering will cause an increase by this factor. Whereas at if it lattice scattering is dominating in this with the temperature, this will be there. So you can see that the mobility or low temperatures increases and it is dominated by impurity scattering, whereas room temperature and above, it is dominated by the lattice scattering. So that is so that this gives us an idea about the mobility variation with the temperature, because that was our idea. See, because we have the whole idea was trying to find out why our mobility, why the conductivity is changing with the temperature. That was the very first lecture on which we are trying to find out that. So now we are in a position. We have seen that conductivity depends on two factors. One is the carrier concentration, and we have seen that carrier concentration. The last lecture, we have seen that carrier concentration changes with the temperature. That is an exponential function. If you look back the expression, you see that there is an exponential function there as far as the semiconductor is concerned. And now you have this factor, especially room temperature and above. So you can see that in fact the mobility decreases with increase in the temperature. But the other one is the exponential factor. So exponential factor will be dominating. Yeah. So this is the one thing we need to see. So what are the conclusions? So this is we have seen that these two factors decides both mobility and carrier constants are temperature dependent. Both are the nature of variation, especially in the case of semiconductors. The nature of temperature dependence of carrier concentration and mobility is different. The carrier concentration increases exponentially with the temperature, whereas mobility decreases with, I mean, room temperature and above. It decreases with the temperature. So now we can say that now we can see like the important thing which we saw in the beginning, the properties which we observed. Now we can see the reason behind that, and we can quantify it also. That metals have a positive temperature coefficient of resistance or resistivity. That means the resistance or the resistivity of the metals increases with the temperature, because metals uh, have overlapping energy bands. So when you increase the temperature, no significant increase in carrier concentration is possible. Whereas mobility of the carriers, because there will be more scattering, phonon scattering will be there, mobility will be decreasing. So in the case of metals, you will be seeing an increase in resistivity or a decrease in the conductivity, because they are related in a reciprocal way fashion. So the conductivity will be decreasing in the case of metals. So we talk of a positive temperature coefficient of resistivity for the metals. We have seen it can be used for making platinum resistant thermometers, etc. So you can, by noting the change in the resistance, we can find out the temperature. More importantly, as far as the semiconductors are concerned, we have seen that the conductivity increases or the resistivity decreases with the temperature, or in we can say that semiconductor, that is the standard definition very popularly used by most of the uh, device engineers, that the semiconductor materials have negative temperature coefficient of resistivity, or its conductivity increases with temperature, uh, typically in a uh, exponential fashion. So you can see that up to the melting point. And the third category, and again, we have seen that it is attributed to the large increase in the carrier concentration. As far as the semiconductors are concerned, they have a filled valence band and then partially filled conduction band. And when the temperature increases, the carriers can be excited from valence band to conduction band. So the carrier concentration can increase, even though there is a decrease in mobility due to increased scattering. There will be a net increase in the conductivity is observed. So we very often we say semiconductors have negative temperature coefficient of resistivity or resistance. When coming to insulators, we have seen that they have a large energy gap. So they have typically um, full valence band or fully filled valence band and empty conduction band, and temperatures even up to the melting point of those materials, very insignificant number of carriers can be excited, so the carrier concentration cannot be increased significantly. So you don't see much increase in the carrier concentration, but the mobility decreases. But there will be a slight increase in the carrier concentration. So you may see many of the insulators with increase in temperature, you may see a small increase in the conductivity, because insulators and semiconductors are similar that way. You may see a slight increase in the uh, conductivity, but it is insignificant. So you very often we say there is no significant change in the conductivity as far as the insulators are concerned. So that is how we see this conductivity. We are in a position to understand it. Now the important thing is here. Okay, fine. Now certain questions arise. Uh, uh, when we talked of these things, like we started with Ohm's law and things like that. So my question is, as far as the semiconductors are concerned, is Ohm's law valid always, or there is some deviation from Ohm's law? So I take few questions. So the next is again a question. Oh, so that will be posted. Yeah. So now I will take a few questions. Yeah, my question is the Ohm's law valid always, or it depends on the electric field or not? Any answer, Bhaskar?
So J is equals to sigma I, so it is also depend on the electric field.
Pardon?
J is equals to sigma I होता है. So the
Change? Ohm's law is always valid. Yeah. You are saying something? Hello? Will Ohm's law valid for any value of electric field? Anybody would like to answer this question? That Ohm's law, any deviation in Ohm's law, as well as where this Ohm's law is coming into picture? Because we have seen the electrical conduction and all those things. Where the Ohm's law is coming into picture? So Nidhi want to say something? Yeah.
Sir, Ohm's law is valid only when the temperature is kept constant.
Only when?
Sir, temperature is constant.
Fine. Suppose the temperature is constant, then my question is, if okay, you brought in that I'm refining my question. If let the temperature be constant, and is it valid for any electric value of electric field? What do you say, Nidhi? Yes.
I don't know how, but it is not
Hello.
valid, sir.
Pardon?
Uh, Sir, Ohm's law is not valid for semiconductors. I don't know how.
No, Ohm's law is valid. It's not always valid. That's all I'm saying. See, actually, we need to see one thing. When we started our discussion, we have said that there is scattering events happening. That is why I went into a bit of elaboration there about the different scattering events and things like that. And
So,
I mentioned one thing. The electric. Yeah, Bhaskar wants to say something. Yeah.
so at high temp, at a very high electric field, it may be the hot carrier and comes
Yeah,
into
how will
play.
you bring in hot carrier effect actually? We are right actually. Hot carrier effect will be there. So, but how will in the microscopic picture we talked of? How will you bring the hot carrier? That's the question because we have. So that means there is going to be a change in the mobility. Forget about the concentration,
So
but
at large,
there is.
when the electric field is too large, so the electron are not
Yeah,
able to deliver that energy to the another electron when there is collision
yeah.
takes place.
So
So it will,
what parameter will change?
so sigma conductivity will not change it further.
No, no. See, we are talking in terms of mobility only. So in the mobility term, only two parameters are there. One is tau and the
So
other is m.
time, the,
Yeah,
the
actually, uh, we need to understand that in our theory, when we developed the theory, we mentioned that uh, velocity is directly proportional to the electric field. That means electric field is acting as a, and I am giving you a numerical that will make it clear to you. The drift velocity is much less than the thermal velocity. So it is only a small perturbation. So whatever happening within the material is not changed under low electric field. That means the mean free path is not influenced by the electric field. Or another way of saying is electric field is not altering the scattering events. Whatever scattering events is taking place, it is its inherent property. Electric field is not involved in that. Only thing is it is giving a small perturbation in the direction of the electric field. So that is why we are talking of the drift. But when the electric field is high, as Bhaskar said rightly, a large amount of energy will be picked up by the electrons. So then they will the scattering rate will change. Electric field induced scattering will take place. So that will change the nature of the scattering. So there's the time tau will be changed actually. Tau will be drastically reduced. So in our Ohm's law assume that if you look into the Ohm's law assume that the mobility is independent of the electric field. It does not depend on the electric field. That is true only if the electric field is low. If the electric field is high, the mobility of the carriers are changing with the electric field. Mind you, I'm not talking about the temperature. We are assuming that the temperature is constant. But the fundamental assumption in the Ohm's law is the mobility of the carriers are independent of the electric field. It is constant with respect. That is, then only it will be the velocity will be directly proportional to the electric field. But at high electric field, the velocity will not be directly proportional to the electric field. And how it happens? That is because of the carrier velocity. The drift velocity is significant. as compared to the thermal velocity. And then it changes the scattering time, scattering rates are changed. So that way the mobility tend to decrease because of that, and with the increase in the electric field. So the one or two events take place. One is the hot electron effect. So we'll be discussing. I'll be devoting a small part of my next lecture on this hot electron effect. Then other one is the velocity saturation. So these two, velocity will not increase; it becomes constant with the electric field. Whereas at low electric field, you will see that the electric field, with the increase in the electric field, the velocity is increasing. That means the mobility is constant. Whereas at high electric field, mobility start decreasing, and the velocity becomes constant. That is velocity saturation. So these kind of phenomena take place. That because these are important because in the microelectronics, when the dimensions are reduced, even at a low voltage, this electric field could be very high. That the velocity saturation, hot electron effect, etc. In fact, it is extensively studied as far as microelectronic devices are concerned. They become important. So that way they are significant. So that is, so we will be devoting some time for that in the next lecture. So I've given two numericals so that you can pick it up from the slides. So you can work it out. So one is to impress upon you the importance of thermal velocity and the drift velocity, the concept. So that will make it clear. So that try to do that. So the in the next we will talk about this uh, the high field effects in semiconductors. After that, we will go to our most important utility of semiconductors, because we will see that the conductivity. Here we have seen that the conductivity of the semiconductors can be modulated with temperature, but that is not of much use. Only thing is it shows certain properties of the semiconductor, but for the practical, it has not much practical application. Of course, there are some applications like you have seen, thermistors are there where we use the temperature sensitive to the semiconductors, just like uh, metal thermometers are there for using, taking advantage of the change in resistance of the metals with the temperature, but that is very limited application. But we will see that most of the application of the semiconductors are coming from adding impurities and controlling their conductivity. So they have a lot of implications. So we will discuss, we'll try to understand those things. So that will be the next session, we'll discuss that. Yeah. So any further questions? Any of you?
Sir, if we assume
Others
it's
are also, our
ballistic
guest members are
transport
also
or
free to,
vacuum,
yeah. Pardon?
if we assume it's a ballistic transport or the vacuum tubes, then it will be
Yeah.
Ohm's law will valid now.
Yeah, there actually it will be, yeah, naturally we can say that. But then ballistic transport within a solid is very difficult. That actually we have seen, remember what is the dimensions required. Last semester we did discuss about the ballistic transport and the dimensions and the electric field. It is possible. Very often, so far, it is only quasi ballistic, near ballistic transport as observed. That means limited scattering events are there. Then it is, see, if it is moving in vacuum, the velocity will be directly proportional to electric field. See, there is nothing to scatter it, because actually this limitation is coming because of the scattering. So if it is moving in vacuum, ballistic transport is as good as the carriers moving in vacuum. So then it is possible. So that is why we can increase speed of the device actually by ballistic transport. But then getting it in a crystalline material, even if the dimensions are small, we have seen that for silicon it has to be around of the order of 10 to 20 nanometers or so. So I don't remember exactly. One can always find out. So it should mean, that means, see, one can the rough estimate will be, it should be less than the dimensions of the device should be less than the mean free path.
30 nanometers.
Mean free path, and
Yes, sir.
pardon. Mean
The
free
mean
path.
free path,
Because
let's
we,
say.
we know the mean free time, we know the velocity, the product will give me the mean free path. So that the dimensions of the device should be less than the mean free path. Then it won't experience any scattering. Yeah. Yeah. Anything else? Yeah. Anybody else? Any questions? Nithi? Then some of the guest members who are still there who would like to ask something.
No, sir.
Okay. So I think then we'll call it a day. Okay then.
Thank you, sir.
Yes.
So you can see it, the two questions you can see it is available at the end of the slides. So that will be available. I'll be posting it so you can pick up those questions and work it out actually. Yeah.
Okay, sir.
Okay. Rashmi, you want to say something?
नहीं नहीं, thank you, sir.
Okay. Welcome.